Hello and welcome to the lecture on hydropower. So hydropower is one of the oldest sources of energy. It's been used for thousands of years to turn paddle wheels for purposes such as grinding grains. But again, it supports more than just the power system. Most installed hydropower capacity is actually connected to reservoirs that might provide recreation, flood control, irrigation, navigation, water supply. So it's often, again, associated with a dam behind it, and then the hydropower is created. So there's other resources that might be associated with it in addition to electricity production. 1882 was the first use of hydropower to generate electricity in the US and Wisconsin. But most of the installed capacity we have now is very large scale projects that were built between the 1930s and the 1970s. And this was the time when we were able to transmit electricity long distances. So it made sense to go to these areas that may be away from population centers where we have a large drop, and so a large hydroelectric capacity due to the changes in elevation for us to build dams and then transmit it to the population centers. The capacity factors for hydroelectric changes year by year. So for example, in 2013, it was 39%, 40% in 12, 46% in 2011. So again, they vary year to year due to hydrologic conditions, water demands for competing use for agriculture, environment and regulatory restrictions. We might not be able to put it through the dam because of different migration patterns in various times of the year. Again, hydroelectric power is driven by the hydrologic cycle. So again, as we have evaporation from the oceans, we have rain and precipitation that then feeds our rivers. And as those rivers go back down to the ocean, that's where we're going to capture our hydroelectric, is during the time that it's going from the river downstream, and we're going to capture that energy. Again, as I said, this is a corn mill that was used with a horizontal axis wheel to use grinding. So again, a water wheel turned, and that was connected to gears, which then grounded the stone. So again, we've used water wheels for a very long time. We also used it for irrigation, again, bringing water from lifting it to raising it up to a higher level, and then we use that in an irrigation channel. But again, it wasn't till the late 1800s where this was actually connected to a generator and used for electricity production. So what we do with the hydrologic dam is, again, we have our intake here. So we're going to send it through the intake. We're going to send it through a penstock to our turbine, and then the turbine is going to turn. That turbine is connected to a shaft, which is connected to a generator, which again, just like the turning of the turbine for using steam for wind, for electricity generation from a coal-fired power plant, a natural gas power plant, or a windmill, it is going to turn that turbine, which is going to induce electricity from a generator, and which is carried through power lines. Again, of our renewable energy sources that generate electricity, again, we have lots of renewable energy sources, but those that go from renewable to electricity, it's historically been the one that's most often used. It counted for about 6% of total US electricity generation and 35% of our renewable electricity generation in the US, again, down from 71%. So it's now only 35% of our renewables, because although we've had this since, again, from the 30s to the 70s is when we built our large scale systems, the other renewables have caught up. So we're producing more energy from other renewables relative to hydroelectric. Again, in the US, we have over 2,000 active hydroelectric dams, varying in capacity, but our overall capacity is about 70 gigawatts of energy. Half of this capacity, over half of our subs, about 40 gigawatts of our capacity, is located in just 3 states, Washington, California, and Oregon. So the Northwest has our largest installed capacity, but the Northeast ranks first in the number of facilities. But again, those facilities are smaller facilities compared to our very large facilities in the Northwest. So again, you can see here, most of our facilities are again, Washington, Oregon, California, with number 4 being in New York and then number 5 in Montana. Our largest hydroelectric dam is the Grand Coulee Dam, which is in Washington State. So again, if we look at the percent of total share of generation, so I didn't mention Idaho as the top 5, but again, it's a less populous state, so the small hydroelectric they have actually achieves almost 90% of their electricity is through this hydroelectric. And again, with hydroelectric, although the capacity, how often they use it changes from year to year, again, it can be used 24 hours a day if needed, 7 days a week. Again, Oregon has a very high percentage as well, and Washington State, again, most of their electricity use, this isn't overall energy, this is percent of the electricity generation. Again, with South Dakota, again, being a smaller state with quite a few hydroelectric dams, by population and by electricity use, again, a larger share. Us in Maryland, we have a very small share of our total electricity met by hydroelectric. And you can see that here, our installed capacity for hydroelectric is about 551, which is actually less than our PV and more than our wind. But you can see here in Georgia and Kentucky, Tennessee, South Carolina, they have much larger facilities, even Alabama. So again, if we look at our total renewable energy portfolio in the US, again, biomass accounts for our largest percent, but hydroelectric is the largest percent, barely, in terms of electricity generation, because again, most of our biofuels, wood biomass, and our biofuels is going to ethanol. Wood is going directly to wood energy, to heat energy, versus hydroelectric, wind, and solar going to electricity generation. So again, if we look historically, we can see here that our wind has taken over right at the same area as our hydroelectric consumption, which again, from 2000 to 2019 has been very consistent, while our wind energy has grown considerably. Again, our biofuels consumption has grown considerably. Our wood energy is about the same. And again, our solar energy is less than our wind and electric. It's expected, if we look at kind of where we are and where we expect to go, hydroelectric is expected to stay about the same, while solar energy and wind, again, are expected to increase. So again, as we said, it varies dramatically from year to year. So if we look at our total output in terms of million megawatt hours, you can see here some years where we might have had drier years versus wetter years. And for various reasons, again, it kind of goes up and down between 250 to 350. So it's still a high range, but within that range, we do see variations from year to year. And again, a lot of that has to do, if we look at the average, we have some years where the average in the Pacific Northwest may be lower than the average, and other years where the Southeast and that production may be lower than the average. So your Alabama and Georgia and Tennessee. So it really, again, although we have a nationwide hydroelectric capacity, those are going to function differently based on how wet they are, how the conditions are in different parts of the US. Now, if we're looking at world, so transition from US to world, again, hydropower is by far the highest, if we look at megawatts of capacity, is our highest capacity. And it has grown, but again, it's been pretty stable, while onshore wind and PV have grown in the world as well as biofuels. But again, hydroelectric makes the majority of this renewable energy power. And we can see here that, again, the top states, #1 being China, #2 being Brazil, 3 being Canada, 4 the US, and then finally Russia being the 5th in hydropower. And we can see here, this is the same thing, but again, China, when we look at being #1, they're #1 by a lot, not just a little. Brazil, Canada, US are all fairly similar. And then we have Norway, India, Vietnam, Japan, and France rounding up the top 10. So again, if we look at the world, while the US is supposed to remain very stable and we don't expect a lot of increasing capacity, we do expect some increase in capacity in the world. So again, if we look at where we are here, wind and solar are expected to greatly increase, but hydroelectric is expected to increase some as well. So if we look at hydroelectric designs, again, the terminology, so we have the head. The head is the higher elevation to the lower elevation. So it has to go from higher to low to release its stored energy. So that height or head is the difference between these two elevations. So the water in the forebay and the tail bay. And so we have high heads, which might be 800 or more feet, a medium head, which is 100 to 800 feet, or a low head, which is less than 100 feet. And again, this is a gravitational energy. This is, again, potential energy. And so the power is going to be proportional to the head times the flow rate. So if we look at large hydros are more than 100 megawatts. Again, that's huge. We have to, again, think of our house, our solar panels in our house, talking about 5 kilowatts. One of these systems is 100 megawatts if it's a large hydro, or more than 100. A medium hydro would then be your 15 to 100 megawatt system. Small hydro would be, again, 1 to 15. All of those are going to fit into electricity grids. Your mini hydro, again, may be anywhere from 100 kilowatts to 1 megawatt, and they can be standalone just to feed a certain area, or they can feed into a grid. But we also have micro hydro and pico hydro. So this is less than 5 kilowatts and 5 to 100 kilowatts. And so these may actually serve an area that stays off the grid and don't necessarily connect to a grid. So again, as we talked about this mechanism, so again, most of ours are going to be behind dams. That's where most of our very large hydroelectric are. And so we're going to have some sort of spillway where we, again, let water go over depending on the time of year, depending on how much water we have behind the reservoir. So we're going to control the water. So we're going to have some go over a spillway, and then we're going to have others, again, the majority of this is going to hopefully go through our penstocks. While some's going over the spillway, some's going through our penstocks. It goes through those penstocks, which is, again, a pipe. And then that penstock is directly connected to our generator. It's going to turn that turbine that are connected to our generators to spin the generator to produce electricity. So again, we have your low head, again, so the water level from here to here is lower. We have our medium head, and then we have our high head reservoir. So again, the length of the penstock and where it brings in the water versus where it's used is, again, determined on the height of the intake to the turbine. So we have 3 different types of systems. So again, we talked about heads, like high head, low head, and types of electricity generation, but we have 3 different types of designs. So we have impoundment. So that's where we have a dam behind it. So the Hoover Dam, the Coulee Dam, these are large dams. They're impoundment systems. The water is kept behind it. We have diversion or run of the river system. So Niagara Falls is an example of those. Most of these are going to be smaller than our impoundment systems, where we're just going to take a portion of it, have a run of the river, and most of the water is going to continue on in the river, not going through our turbine. And then we have pump storage. This is a 2-way flow where we have a lower reservoir and a higher reservoir. And we're going to pump it. We're going to use electricity to pump it to the higher reservoir and serve as a battery. And so then when we want to use it at 4 o'clock on an August, we can then send it back down and use that extra electricity at the time at which it's needed most. So first we'll go through the run of the river systems. So again, the force as it comes through applies the current for the force of the current applies the pressure. So again, in the storage system, it's accumulated in dams, and then when it's released, when the demand for electricity is high. And again, those, if it is a storage system, an impoundment system, these reservoirs behind can be used for recreation. Also, though, we need to realize that, again, with dams, we might have silt and metals accumulating behind the dam, so we need to think about how we're managing the dam and the aquatic life behind the dam. So again, first, our run of the river systems. So here we have a river. So the river again is coming through. So most of the river is not impacted by this hydroelectric system, but we do have a weir that's going to divert some of the flow, and part of the flow is going to go to our intake valve, and part of the flow is going to keep going down the river. So in the intake valve, it's going to take part of that flow, send it down our penstock. So we still have our penstock there, and then it's going to go through our turbines and generators in our powerhouse to our transformer. So here is an example of one in Alaska. So again, most of the river is going over this big waterfall, but part of it is coming in right here to our intake valve, going through our penstock, which you can't see, and then it's coming out at our outlet right here, which again, so the power of the river's turning, the current is actually kind of turning it here, and then we're letting it go here in our outlet system. For our pump storage, again, it's going to be an impoundment system, but the difference is this impoundment system is going to be a two-way instead of a one-way. So what's going to happen here is here we have our intake like we normally would, and we're going to send it through here and create power. But the difference being is we actually have a valve where we can pump it back from our discharge area, back it to our reservoir, and raise that water back up. So for this, at a time of low demand, again, we talked about a lot of electricity that's kind of we make, but it's not actually being used. So what you can do is that extra electricity that's not needed, that surplus power, can then go to drive the water, to run electric pumps to drive the water from the lower reservoir to the higher reservoir. And then during the day when we need this power, it's going to work in the opposite direction and it's going to pump here. So when we operate as a pump storage, we end up not necessarily generating extra electricity. We're mainly using it as a battery. When we have surplus electricity, that electricity could be generated from other hydropower dams. It could be generated from wind, from solar, from natural gas. But when we have extra electricity, we're going to pump it. And then when we need it, and the thing with this is we can turn it on immediately. Because again, unlike getting a power plant, a natural gas power plant, we got to heat up our source, our steam. We have to heat up our water so that we can get our steam to get it going. It takes time. This happens immediately, and then the power is available to the customer. Again, so when we think about meeting those peak dams, that's what they use a lot of these pump storage, is when all of a sudden we have a lot of demand and we need it right now. So again, hydroelectric dams, they start easily and quickly, and they can change. We can turn them on, turn them off, turn them on, turn them off. We can, go back and forth however we want to. It's very easy to start it and stop it. So often they might complement a large thermal plant like a coal, a nuclear, or natural gas plant, which might have that base load, and then this would just kind of pick up those peak demands, what they call, and would save a lot of oil, natural gas, and coal, because the idea is that we are not having to get a whole nother stock on, get everything ready to meet that peak demand. And so again, our pump storage fleet, we have about 42 plants, so a lot less than our 2,000 hydroelectric plants, and it serves about 21 gigawatts of capacity. So here's an example of one in Colorado. It was completed again in 1967. It has two 162 megawatt systems, so it's 324 megawatts total. And so again, when it's needed, the water can be pumped uphill at night, and then it flows downhill during the day to help XL Power, is the power company there, to meet their surge demand. And again, the efficiency is usually 70 to 85%. So it is efficient as a kind of a battery storage. What pumps up, they get 75 to 85% of that electricity back. So here's an example. So here's when they're actually running the pump. So this is 0 hours. So this is midnight. So from midnight to 6 a.m., they're running the pump. And then here, starting about 7 a.m., they start to actually produce power. And then here they didn't need it for whatever reason, so they turned it off and they pumped for a little bit. And then they went back to get this very peak hour power that they needed throughout from, it looks like about 8 till about 1700. And then they didn't need it, and then they needed it again in the evening, and then they started pumping again. So again, it can go on and off very quickly. Again, it should be noted that dams, only a small percentage of all dams in the US actually produce electricity. So most dams actually don't produce electricity, and they're constructed solely to provide irrigation and flood control. But dams do, whether they're for electricity or not electricity, they do change the environment by affecting natural habitats. So again, we think about salmon that have to swim upstream, but dams can get in their way. So we do have fish ladders to try to help to address that, which has been with varying success. And then again, as we mentioned before, we also have metals and sedimentation and other things that can be stopped by the dam, whether or not that dam is producing electricity or not. So if we look at actually the construction of dams, national inventory of dams, most of them are for recreation, 11% for irrigation, for public water supply, 15% for flood control. Some of them are for farming systems, so whether it's water for animals or actually for aquaculture. And only 2% of these dams are actually for hydroelectric. So we look at the world's largest dams, again, Three Gorges being the largest, which was completed in 2009. And again, we are talking about 18,000 megawatts. So it's a huge system versus the Grand Coulee in the US, which is our largest dam that was completed in 42 with an upgrade in 1980, which has almost 7,000 megawatts of electricity. So here is the Hoover Dam. So if anyone, you can actually drive over it if you're driving in Nevada, between Nevada and Arizona. And so again, Las Vegas is not so far away from the Hoover Dam. And so here we have, again, the reservoir behind it. We have the dam here, the spillway if it's needed, and then most of it's going to go through the penstocks and then going to come out here after electricity is produced. Here is the Three Gorges Dam. Again, it's a much larger system. And so here's it coming out of the penstocks. And again, with the Three Gorges Dam, they have a lock system because this is a navigational river. And as we said, most of it's going to go through the penstocks and not necessarily over the spillway. And so they actually have a lock system, kind of like the Panama Canal, where they bring the boats, they bring a lock system, bring them up and over, and then let them down at the lower elevation so that boats still can be a navigable river. This is a dam system that's actually the border between Brazil and Paraguay. That again, you can see they have spillways, but most of the water is coming here through this penstock system and generating electricity. Here's another one where you can see some of it's coming over the spillway here. This is in Venezuela. Here is the Grand Coulee Dam. Again, this is in the state of Washington in the US. And that's it. So we'll talk more about the environmental implications of hydroelectrics and dams, especially around the world. But this is the basics of the design and the output of hydroelectric in the US and the world. Thank you.